Alright, to get started we're going to go ahead and open up Google Colab and we'll start a new notebook like you see it right here. So what we'll do first is construct a file called gamedata.csv, and it's a comma delimited file. This is the file right here. I called it gamedata.csv, and it is a file with some headers at the top. You can see health has knife, has done enemies and behavior, and this represents behavior in a game. So the first field is health with, we can see it can be 2, 1, or 0. Then we have has a knife, has a gun, the number of enemies we have, and what our actions should be. What we're going to do is train a neural network to predict the values of behavior for a set of inputs in it has never seen before, so you want to go ahead and create this file right here and call it gamedata.csv. In order to get this into Google Colab, we have kind of some Google Colab only code here. What we're going to do, we're going to import the library, which is just called files, and what we're going to do next is put a little code here to upload the file. You can run that cell, and you'll really only have to do this once every session. So as soon as your session expires, then you'll have to reload your file again. So I'll go ahead and upload it now, and we can see that the file is indeed uploaded. Before we start, we'll go ahead and import some libraries here. The first one is going to be pandas. We'll import that library, and then we're going to import the Tensorflow libraries. I'll put these all in one cell right here, and you can go ahead and run that cell. Then the next ones are from scikit-learn. And these are going to provide us a couple helpers for setting up our training data. And I'm going to import datetime in case we need to produce any files that need a file name. I'll just use the date and the time for it. All right. So all we have at this point is a file uploaded, a bunch of libraries imported. So what we can do is we can read the data using pandas. We just have this pd.readcsv and it reads the data. Now in Jupyter Notebooks, anytime you have a cell and you just have an expression here like a variable, it will display the value of that expression right here, which is just a variable, and we can see that it correctly read in our CSV file. You could also print it in case you're not working inside Jupyter in a book like this, and it does pretty much the same thing. All right. Now, just in case any of these columns have spaces in them, we can go ahead and strip the column names. And you can see right here, mine actually does have spaces. So if I would have made my file look like this, I wouldn't have to get rid of these spaces. But I'll show you how to do it anyway. So all I'll do is just strip it right here, and I'll just resave those new columns names, with the spaces gone. All right? We do have a nice function called describe, so we can take this data and describe it like such, and we get some basic statistics, and it's a good idea to look at your data first and make sure there's no ridiculous outliers. You can look at the min and max for any of these. So if we saw a max that looked out of range, maybe like a 20 or something right here by the enemies, we might want to make sure our data is correct. And we also get an average mean here and a standard deviation and some percentiles. So looking at our data, again we can see that we have numeric data for all the fields here except for the behavior, which of course is categorical. So what we want to do is make what's called a one-hot encoding for categorical data. So for example, we have these options right here, and I'm going to put in a text cell for this. So we have these examples. We have wonder, we have hide, we have attack, and we have run. So we have 4 possible actions that we can take, and we need to have numerical values for these. But of course, we don't want those numerical values to have any quantifiable meaning to them. So what we're going to do is we're going to encode these, and the way it's going to work is something like this. we're going to have a vector of bits, and the vector of bits is going to look something like this. So we can stick a 1 in the spot that represents that selection, right? So this isn't code, this is just in the comments in the markdown here, and we're going to have hide, right? Might be this vector right here, could be oops, this one. Right. Doesn't really matter as long as they're all unique. And what we would have is a set of bit encoding that looks like this. And this is called one-hot encoding. And to do that, we actually have a helper function that can do that for us. And what we do, we make something called a label encoder. I'm just going to label it label encoder. I could have called it behavior encoder or something like that. I'm just calling it label encoder. And what we're going to do is next essentially choose the field that we want to encode, and we want to encode, of course, the behavior field right there like such. And we can go ahead and take a look at the data. Again, we can just look at the raw data, and you'll notice that it looks like it has a value here. Now, this is not really a numeric value, this is just a number assigned to that category. So behind the scenes, we actually have a vector. And they're just assigning 3 to be this vector, and 3 to be this vector, and 0 to be this vector. Yes, and I'll show you how we can look at the one-hot encoding here in a second. We will convert behaviors to categorical like this, and what we can do, we can actually see the vectors for each of these. So it looks like wonder. We can see it. Right there has the bit all the way on the right set. So every time we see wonder, we're going to just see the bit all the way on the right set. So what's that? Maybe the 6th one from the bottom right. We can see it right here. And any of these only have one single bit set. So what we'll do, we'll just kind of get rid of this behavior column, right? So I'm just going to get rid of this behavior column like this. And if you want to see it, to see that it's actually gone, we can look at it like this. We can say print training inputs like this. We can see that this is our inputs now, so we want to separate our inputs and outputs, right? So this is, of course, supervised learning. And the category label, of course, is behavior. And then, of course, our outputs are going to be the behavior field. So after that, I can just print the outputs just so you can see that, and probably put a line break in there so you can see it a little bit better. Okay? So you can see that these are the outputs right here. Okay? And this is just a categorical idea. I'll show you how to add the one-hots here in a second. All right? So what we need to do next is divide this data between training data and test data. So any time that you have data that you want to use for training, usually you train it on about 80% of it. And we want to kind of pick it so that it gets a variety of inputs. So for example, we would not just want to train it on the first several here, because none of these have 0 health, and there's only 0 health at the bottom, right? We wouldn't want to just maybe use the latter half as well down here, because we wouldn't have any with high health, or maybe we only have 1. So we want it to have kind of a variety, and what can happen is we can have some helpers that can help us accomplish that. Here. So I'll add another code cell here. And what we're going to do is we're going to use a function called train_tests_split. And what this will do is it will take our set of all of our training inputs, which is right there, and then we want to give our outputs. Now, for our outputs, we want to go ahead and use this right here. Now, we could have just replaced this field, whatever. Then for our outputs, we can put our one-hot behaviors in here, right? So that we have categories that are essentially binary encoded. Next, we're going to pick our test size right here. And Python's a little unique, where you can pass things positionally and you can pass them named. So I'm going to name this one here. 0.2 means 20%. So that says that I want 20% to be part of the test set. And I want 80% part of the training. Now by default, it'll just kind of use a random number and it'll choose these at random. So far, 20%, I might pick this one and maybe number 8, maybe 14, and maybe 17. If you want that to be repeated, you can give it a seed. So there is something called a random state, and this is essentially a seed value. Oops, it's random state, a seed value you can put in, so you can just, pick a number if you want. It doesn't really matter, and then you can pretty much, every time you run this, you'll get the same exact set of values in your training input, the same 80% in your training, and the same 20% in your test data. So I'll just put a number in here. I'll just put 1, 2, 3. Oh, damn. Oh, dear bloody me. I forgot to assign that. So, by default, it's an expression. It prints it to the screen.
So this returns actually several sets of data. We can see them right here. This is going to be our X-training data. This is going to be our test data. So here's all training data, all test data for the inputs, and then here's all of our outputs. So what we want to do is assign the return. So in Python, of course, it can return multiple values. And the way it does it, you just assign them like this, and you separate it with comma. So there's going to be equal sign there, and this will be X test, this will be Y train, also be Y test. I like that. And then I can just run that. And then, of course, they're all assigned here. So any one of these, I can just print it and take a look at it. So there's all of our training inputs. There's all of our test inputs. So it picked record for 11, 14, and 8. So I can run this over and over, and I'm always going to see this same values get used. It's always going to pick the same ones, right? If I pick a different seed here, I get different ones picked right like that. So this one always picks 3, 1, 4, 5, and 17, right? I change that, and we see different ones. If you just get rid of this completely, of course you'll see that it'll just pick randomly every time, right? But sometimes when you do testing and you're trying to do some R&D, you might want to have that predictable. So it won't hurt to just pick a value for this in case we need to reproduce the same test again. Then, of course, we have the training data there. That's the output for our training data. And then we'll have our output for our test data with that. At this point, we're ready to make the model, so we can put a little comment here and create the model. This is all marked down. All right. So we can see something like that. So we'll do this. We'll just call our variable model, and we're going to use the Keras sequence models. And what we do, we just start putting in layers. I'll just make a little space here. What we're going to do is put in a layer right here. We're making a layer using the dense function. And what the dense function means is that every output is connected to the next layer's input. So the input of any node in the layer will be connected to every single output in the previous layer. That's what dense means. Sometimes we call it a densely connected network. Now the first parameter is how many nodes we want in there. So we can arbitrarily pick something. Maybe I want 10 nodes in there. And what we need to do next is list how many. What we need to do is list how many inputs are going to be connected. The model is not going to know, because it is the actual very first layer. So what we need to do is just say, hey, we have 4 different inputs. So right here, we should just say, I have 4 because we have health, has, knife, has, gun, and enemies. So that's where this 4 would come from. A little bit better way to do it is just to make it a variable. What we're going to do is we're going to say the input shape equals. That's just say input underscore shape equals 4 comma nothing, and that basically says there's 4 inputs. But rather than hard coding, you can just say, give me the shape. So you can essentially say, give me the shape of this right here, and we want to essentially return the dimension of 4. So shape is just the dimension here. What is the shape this? It's going to be xtrain.shape, one like that, and that's going to essentially result in a 4. And what I can do is just to show you this, we can see that the shape is 4. This is making 10 cells, but allowing for inputs into each of these cells. That means that health is going to be connected to 10 different cells. Knife is going to be connected to 10 cells. Hasgun is connected to 10 cells, and so on. We really only need that for the first layer because it can't really be implied. So the next parameter is going to be the activation. Then comes some of the art in designing a neural net.
And now a word from our video sponsor. Have you ever been so bored in your artificial intelligence course that you started daydreaming about anything other than algorithms? Well, snap out of it, because we've got the ultimate classroom distraction, the AQKILO Squirrel and Unicorn Finger Puppet Set. Perfect for turning a dull lecture on neural networks into a puppet show of epic proportions. You'll be reenacting battles between squirrels and unicorns while your professor talks about backpropagation. Who says you can't multitask? Got a group project where you're completely lost? No problem. Let these puppets do the talking for you. Yeah, Professor, the unicorns totally understand deep learning better than we do. And the best part? They're made of premium quality polyvinyl chloride, eco-friendly and non-toxic, perfect for those long, boring computer science lectures. Trust us, they're more fun than debugging code. Don't let your fingers suffer through boring lectures any longer. Get your Aquilo Squirrel and Unicorn Finger Puppet Set and let the magic of distraction take over. Not responsible for failed exams, missed lectures, or excessive puppet show enthusiasm. With a brand like AQKILO, you can't go wrong. Because sometimes you just want something in your hands to play with. Consider leaving a like and subscribing to this video. If you do ever want to get your very own Squirrel and Unicorn Finger Puppet Set, consider using the link in the description. And now, back to our video.
We have to figure out how many layers do we need, and how many in each layer. We can start out kind of small here if we want to. And we can just add one more layer, and let's just put maybe 5 in the next layer. Now, we're not going to have to put the input shape because this is a dense layer, and the inputs of this one will contain all the outputs here. So that means every one of these 5 cells are going to be connected to every cell in the previous layer. So all 10 of the ones in the previous layer. But we do need to say what the activation is, and we're picking ReLU because these are numeric values. Here's our layers. Our inputs are fed into this very first layer right here, and then we have another layer after it, right? So we have kind of 2 hidden layers there, and then we want to have one more layer in the output. Our output is categorical. It is still dense, and we have to give the shape of this one right here. So we have to say, how many different output categories do we have?
so we know we have 4. We have run, hide, attack, and wonder. So instead of again hard coding that, it's probably better to just read the shape, and we can just read the shape of the one hot like that. And again, this is essentially the value 4 also. So it's just coincidence that we have 4 unique inputs and 4 unique outputs. We can see right there that 1 is also 4. For this one, since it is categorical, we want to use a soft max activation.
So this is the output layer for multi-class classification. I forgot to put a comma here, and I also forgot to put in this is an array. So there's our model. So our model is basically this design, this network right here, with this dense layer in this dense layer. So one of the things we can do is get our model summary, and all that does is explain our model, the type of layer, the shape, and of course the number of parameters. We'll take a look at this right here. You can see that it gives you a little chart. All of our layers are dense layers. That means that it's fully connected. Every output is connected to the input of the next layer. It does give the shape, and we saw that we have 10, 5, and 4. And then, let's take a look at the number of parameters. So this is going to tell us kind of how complex our model is getting. The number of parameters, I'll show you how it figures that out. It's going to be the number of inputs times the number of outputs. So what this is, it is the number of inputs times the number of outputs. And then you add on the number of outputs. So we'll just take one, for example. We'll take this first layer right here. So for the first layer, we have 4 inputs. It can be health enemies, has gun, has knife. So there's 4 inputs there. And the number of outputs are 10, which we can see it right there. So this is 40 plus 10. That gives us 50. And that's how we get this value right there. And why do we have that? Well, so really what this comes down to is the fact that we have the weights right here. So we need an input, and we have every input having a weight. So every input goes into 10 different cells. So of course we have 10 different weights for each input. So that gives us 40. And then we have to add on the 10 biases for each of those. That's where we get the 50 parameters. Looking at the second one, the shape of this one is a little bit different. So that means every time it has to train and do back propagation, it needs to adjust 50 parameters in this layer, 55 in this layer, 24 on that layer. For the last one, next we do a task called compiling the model. We're going to compile this model. We just say model.compile. And here we have a couple hyperparameters. The first thing we'll pick out is our optimizer, and we can see that the default value is our mass. But for this one, we're going to use an Adam optimizer, which is some sort of flavor of gradient descent. Then we have to compute our loss function, and we have to pick something that mathematically makes sense for categorical data. For categorical data, we can pick categorical cross-entropy. We're going to put one more thing in here. We're going to look at our accuracy as this thing trains and see how well it's training. Here is where the magic happens. This is training the model in our next line here. So what we'll do, we're just going to say model.fit. Model.fit means train the model. Now we do need to give it the inputs for our training data, and that was xtrain. And our outputs for the training data was that's ytrain. Now we can pick how many epochs we want. I'll just pick 10 for now, and we'll see how this does. Now batch size, that size, is how many of these records it's going to try to put in at one time. This is a very small model. It's a very small amount of input, but we have to be concerned that not all of this data would fit in memory if this was a larger model. I want my batch size to be 10. We put in 10 records at once. Now, ideally, it would be nice to train on all the records at once. So what it does is it will put in a size of 10 records, and after those 10 records, it will go back and make changes to the weights. Now, if we have a batch size of 1, that means that adjust the weights after every single input. If we do it by the size of 10, it adjusts the weights and accumulates the error and then makes changes after 10 records have been processed. We can easily fit all these in memory for this example. You can actually choose a batch size bigger than your number of records, and it handles it okay. So, for example, I only have 18 records here. It's not going to break anything. The validation data is going to be X test and Y test. Oops, I forgot to name it right here. It's like this. All right? So this is a data set here. We can set the verbosity here. You will need make log your data. This should be enough to get started.